Hello everyone, I'm Dr. Sri Banerjee, core faculty for the College of Health Sciences and Public Policy, Walden University, and in this video I want to be going over the prospects and challenges of multi-omics data integration in toxicology. So as for starters, it's good to take a look at the abstract always and make sure that you understand what we'll be talking about. And there's a lot of different aspects to this when we're thinking about multi-omics. Something that some of my colleagues haven't thought about yet. So this is more of a kind of a overview of this. There's a lot more detail, and this is probably more of something I've been studying for years, and actually got introduced to it in a conference that was held in Philadelphia, where the whole conference was about omics. So what is it? You might have heard it very many times, but the evaluation of methods for integration and analysis of multi-omics. I'm going to go over a little bit more detail about each part of the multi-omics and how to kind of tie it all together. But just multi-omics data integration can considerably improve the confidence in detecting a pathway response. So this is something that is important to understand. Because multi-omics has a different way of organizing things. So looking at some of these data sets, which may or may not be available at this time, they may lead to some dead links. So just try some of these out. There's a lot of good acronyms. A European Center for Ecotoxicity and Toxicology of Chemicals. We can take a look at this and see if this is one that's available. And I believe ECETOC, I think I missed a letter here. Here we go. Just wanted to help you take a look at some of these. And here there is kind of a way to take a look at this and understand what scientific concepts and methodology is being used. So there's a lot of components to this. It's beyond the scope of this lecture, but just looking at this and understanding what their mission is and what they're doing. So as far as what we do, it says we shape, we expand, and we communicate. Science for public good, collaboration, these are the values. This is a little bit different than what was available, but this covers synthetic chemicals which may affect individuals. So now going into the single omics technique, where transcriptomics can detect biomolecules of one type, and also called one layer. So it uses somewhat of a geospatial field. And so a single omics technique will detect biomolecules. Applying single omics, it's in response to a toxic end, and a non-continuous design led to the ID of biomarkers for certain exposures, but not to a systematic understanding of toxicity pathways or adverse outcome pathways. So this goes into a lot of the exome tox. Is not too, I believe, is not available, but some of this is. So multi-omics in toxicology. finally, now we're integrating the two. So you'll see a single omics technique, which will measure biomolecules of a specific type, for instance, RNA. Also, single omics technique will not even detect the entirety of biomolecules of one type, but a smaller subset thereof are more similar biochemical properties. So that's RNA, and you can see Figure 1a with some of these. 1a is showing how all of these work together, the DNA, RNA, metabolites, amino acids, and phosphorylation. So kind of, this is the single omics technique, putting it all together. Now, the detection of short and long chain RNAs, or of short peptides and proteins, it requires different transcriptomic or proteomic approaches, respectively. Only the use of multi-omics, also called cross-omics approaches, allows for directly detecting a significant fraction of a pathway's response to chemical exposure. So this is divided into transcriptomics on the top left, where transcription is not complete. So transcription is going from RNA to protein. So going from RNA to protein, that's where the problem is. Now here on number 2, proteomics. So that means, so what do you have? DNA to RNA, and then messenger RNA translating to protein. So this sort of creates possibly misfolds, and for instance, sulfur bonds and some of the other bonds may be not beneficial. And then you look at metabolites. And so this is actually coming from what is bound into the active transport proteins and channels. So that's metabolomics. And finally we see, and this is also looking at how much data. So as you can see, this is the most type of data. This is phosphoproteomics. So there's multiple, there's phosphorylation defects, and then also in terms of transcription and in terms of translation, excuse me, that's what this is. So here this goes into more detail. So this is how they're organized. 1b illustrates which components of a pathway and how perturbations of a pathway respectively are detected by different omic layers. So for instance, detecting the pathway response to chemical exposure, you want to look at transcriptomics, proteomics, phosphoproteomics, and metabolomics, and to consider epigenomics for specific cases, and also give a rationale. So then this article goes into the details of transcriptomics, proteomics, metabolomics, and then epigenomics, post-translation modifications of proteins, and then single-cell omics. So that also methylome sequence, RNA sequence, ATAC sequence. Now looking at toxicology for research questions, that's an interesting sort of area. And then there's time series data, flexibility of integration methods, and then publicly available web-based tools like Paintomics, Impala, or OmicsNet. So here are case studies and then pathway analysis. So there we have it. There's this one's a kind of a long article, and I encourage you to read parts of it and to kind of skim through it, because it's sometimes very difficult to understand. So just go go through it, and then they go through some conclusions, which is important. So just read through it and you'll get more information. Thank you for listening.